Hello everyone and welcome to Rational Science, the only site on the internet that does physics, real physics, genuine physics. Everybody else does particles and concepts. That's what they move around. And here we talk about something else. We're saying all atoms, all matter in the universe is interconnected, physically interconnected. Okay? And so we arrive at a different universe than all these other people. Okay, last couple times, maybe over a week, been talking about the origin of the universe according to mathematical physics and also Christianity. Okay, so we have these two versions. And I also looked at last time how some of the matter, how some of the things were created along the way until today. Okay, and again, I compared to Christianity against, in this case, quantum mechanics, because it's quantum mechanics that tackled this problem of what happened at different stages. And today I'm going to add another ingredient to this story, okay, especially to the story of creation, okay, from a mathematical physics point of view, okay, which is not physics at all, as we will see. Okay, so the ingredient I'm going to add is called the instanton. Okay, the instanton. You say, what the hell is an instanton? And you might even accuse me and say, well, Bill, you're just going to give us your version. No, today you're going to hear it from the horse's mouth, from the people who proposed and still propose to this day the instanton. And, forget about the Higgs. Everybody thinks that the Higgs is the God particle. No, the instanton is the God particle. It's the one that triggered creation, according to mathematical physics. And, I've had this article from the Astronomy magazine, and this dates from 1999. It says How It All Began by Stephen Hawking and Neil Turok. So they're going to tell us how the universe began. They're going to use the instanton as the little seed that gave origin to everything. Okay, so what I did was put the article in pictures so that you can see more or less what they were talking about. We're just going to breeze through that. And you're going to see how the instanton gave origin to the universe, or how the mathematical physicists, even to this day, are working on this same stuff. Okay, they're still working on the instanton. So the instanton is alive and well. Okay, it's the god of mathematics. Okay, so here let's go with the first one. It says how it all began. Okay, and the title of the article was "Give Peas a Chance." Okay, give peas a chance. And here we have the two of the ideas that were included in that article. One comes from Neil Turok, which was like a right-hand man to Stephen Hawking. And he said, one can predict everything about the universe from this initial instanton. The calculations are very precise. And then we have on the other side someone who created this inflation that I talked about the other day, inflationary theory, that says that the universe somehow exponentially increased in size in the first few microseconds. And his name is Alan Guth, or Guth. And he says the Big Bang Theory proposes no answer at all to the question of what banged, how it banged, or what caused it to bang. In other words, he's saying we cannot really explain how the universe came into being, how matter arose from absolutely nothing. And so here's another page and another two people who don't agree completely, and one is Stephen Hawking, which died a couple years ago, and Andrei Lindy. He's a Russian who teaches at Stanford University. Pretty popular guy in the world of mathematical physics. And Hawking suggested that such a theory might explain no less than the initial conditions of the universe itself. And Lindy, on the other hand, he's got a little reservation. He says, it is such an esoteric science, creation from nothing. It's like a religion. Okay? And so, yeah, the question is whether creation from nothing, you could call it a religion. You could just say it's an irrational explanation, irrational theory. Okay? Okay, and here are the models because there's different models to compare against so that you can get an idea what these people are working on. Okay, and the first one, and I'm going to talk about that a little later as well. In the no boundary hypothesis, Stephen Hawking and Jim Hartle envisioned time, depicted here running up the side of a cone, emerging from space around the cone. On the other hand, we have a little later the Hawking-Turok model, a wondrous object dubbed the P Instanton, which contains a P's mass jammed into 10 to the minus 30 centimeters, sprouts into an infinite open universe. Okay? And then the model that these other mathematical physicists support, people like Lindy and so on, a lady known as Professor Kalosh. Okay, she also works at Stanford. They come up with these models, which is the multiverse. Okay, in the multiverse theory, our universe may be but a tiny part of a vast bubble that inflated out of a pre-existing region. Similar bubbles have been forming since time immemorial. Okay, so these are essentially the competitors in mathematical physics. They have no other ideas. This is it. So if you're wondering, how the universe came into being, if you actually believe that that's what happened, that matter somehow came in from the void, well, this is it. There's no more than these theories out there. There's modifications to these theories. There's different branches, but this is it. This is essentially it. Okay? Today we're going to look at how the P Instanton, relates to this. Okay, here's the Hawking-Turok Instanton, okay? And this is also out of that article, so we're going to let them talk. It says, what emerged was a proposal dubbed the no-boundary hypothesis. It can be imagined with a little help from a simple geometric shape, a cone. Imagine that the cone represents the evolution of the universe. Time runs up the side of the cone, as you just saw a minute ago, okay? While space runs around the cone. Okay, keep that in mind. Time goes up on the side of the cone and space goes around. The space is the circle, so to speak, a bunch of circles, going upwards. Okay, as you go up forward in time, the width of the cone space, right, enlarges. The origin of time and space is the point at the bottom, okay? In the traditional Big Bang model, this is the singularity. Okay, so we start at a singularity, it expands, and what they're saying is that the circles that form the cone, that's space. And time really flows along the edge of that triangle, that cone, okay? But in quantum physics, there is no such thing as a precise point. There is an uncertainty to it. To visualize this, imagine that the point is rounded off. Okay, so here we get into the hocus pocus. Picture an extreme blow-up of the tip of a ballpoint pen. This is just what Hartle and Hawking's path integral predicted as the most likely configuration for the universe at its birth. Rather than the time dimension up the side of the cone, here it is, beginning at a discrete point, it emerges from the space dimension around the cone. Okay, what they're going to do is they're going to put time together with space and say that the circles that form the cone, that is not only space, but it's also time. Okay, so they're going to have all these rings going upwards, and that's going to include both space and time. Time is no longer along the edge of the cone, in other words, okay? And just as there is no point on the surface of a sphere where one can say the sphere begins, there is no distinct point on the hemispherical, rounded off bottom of the cone where time or space begins. There simply is no starting point, and there is no distinction between space and time, or even past and future. In essence, Hartle and Hawking proposed that the universe inflated out of the bottom of the cone. What do they mean by that? They mean out of nothing, because they're saying that you can't have a starting point on a circle. You have space and time, they're in a circle, they're at the bottom of the cone, but the cone is not a point. It's got a rounded point. And because it's got a rounded point, and that rounded point has a circumference or circle or whatever, and that circumference or circle includes both space and time, neither space and time had an origin. Okay? You see where they're getting to this. They're trying to show that the universe did in fact start from nothing, because time and space, they're part of a circle, and where's the beginning and the ending point of a circle? That's their logic. I guess you can call it logic, okay? Okay, so let's see what they're proposing here, pictorially, okay? In the instanton, they're saying, look, we have time as circles around the instanton, okay? On the other hand, you can see in comparison to the cone, time runs up the side of the cone. Here it's going around the instanton, and since it's a circle and there's no beginning and end to a circle, they're going to claim that time and space had no beginning. Just like, there's no beginning or end to a circle, okay? That's what they're gonna. That's their argument. Okay? And here they more or less tell you what it looks like. It says, "What does this new creation model look like?" They asked Turk and Hawking, and had imagined it using math. Well, it's small and round, but not perfectly round, and it has little dimples, something like a pea. Turk replied. Okay, so space and time are blended together in the pea, such that its bottom half is just like the rounded off tip of the cone in the original Hartle-Hawking no boundary model. Here again, time emerges from the geometry of space, and there is no discrete beginning to either. Okay, you see what they're doing here. This is now, by the way, this is all handled mathematically. It's not like you can imagine this in any way. Maybe you can imagine that there's no beginning and end on a circle. Okay? Circular argument. Yeah, there's no beginning and end to a circle. There's no beginning and end really to any, like a triangle or a square, because where do you begin? At the corner? Well, that's arbitrary. I mean, you really don't begin on any two-dimensional figure anywhere. You don't begin, you don't have a starting point. And the same goes for three-dimensional geometries. Take a cube, take a sphere, where's the beginning, where's the end? So the question is whether this logic makes any sense. But this is what they're going to talk about. This is how they're going to gear their math around this notion. Okay, so that's where we're at. Now, theirs is not the only instanton. They had one type of instant, and here's another one, probably just as famous, or probably the one that was there before theirs. Okay, they improved, I guess, on this one. This was the Coleman de Lucia Cosmological Instanton. And it says, describes the creation of an open universe via a bubble nucleation. Okay, they're going to do bubble nucleation. This is a little bit of different concept, okay, that you're going to see in a minute, because I'm going to illustrate it, okay. Matter in the early universe is initially in a state known as the false vacuum. False vacuum, okay. Everything from mathematical physics is false, even the vacuum, okay. A false vacuum is a classically stable, excited state which is quantum mechanically unstable. What does all that mean? It means it's not nothing. It's not a vacuum. It's a vacuum that's got something in it. That's what it is, okay? And here you get a, I think I got a picture of that. There it is. If I can put it up here. Okay, here's the famous false vacuum of quantum, okay? And they explain, this is out of the Wikipedia, it says the energy E, okay, that you see down at the bottom there, the y-axis I guess you could call it, is higher in the false vacuum than that in the true vacuum of ground or ground state. But there is a barrier preventing the field from classically rolling down to the true vacuum. Okay? Therefore, the transition to the true vacuum must be stimulated by the creation of high energy particles or through quantum mechanical tunneling. Keep that tunneling in mind. We're going to talk about that a little later. But you can see what happens. You got the false vacuum. You can't get to the true vacuum. The only way you can get to the true vacuum is what? Tunneling, or if somehow pushes this vacuum in such a way that it overcomes that little blip, that little mountain. Okay? Okay, continuing here, it says, in quantum theory, matter which is in a false vacuum may tunnel to its true vacuum state. Yeah, which is what they explained there. So you can tunnel through. And false vacuum decay proceeds via the nucleation of bubbles. Inside each bubble, the matter has tunneled. And bubble interior is an infinite open universe in which inflation may occur. Okay, inflation, remember that's what Alan Guth came up with, so they had to explain that, how that came about. Okay, so this is essentially what these people are saying. Okay, here's an illustration of this. Okay, here you have the false vacuum and you have the true vacuum. As you can see on the left-hand side, you have more false vacuum than true vacuum. You know, all of it is false vacuum. But as time proceeded, okay, you have more true vacuum, or the true vacuum is expanding at the expense of the false vacuum. And you would think that we arrived today where most of it is true vacuum, but when you ask all these people, they say that the true vacuum out there is made of particles. So I don't know what they've achieved with this, but just so that you know, there are different notions of this instanton theory. There are different branches of it, okay, and they're still developing some more. They're just brainstorming ideas and developing them mathematically. Okay, so that's where they're at today. Okay, here's a punchline from Neil Turok and Hawking, and it's also from the article, and that gives you a pretty good idea where they stand. And nothing has changed really till today. Of course, even if Turok and Hawking are onto something with their P instanton, it would still leave a very fundamental question unanswered. How did the P get there? Yeah, that's what we all want to know. Did God create it? Turok and Hawking say it's meaningless to ask the question. Geez, just when the question that they needed to ask, that it's meaningless, it's unscientific, right? There is no outside the P, no before the P. It just is an object implied by the very laws of physics. So they asked the next question, what created those laws? How did the laws go? You know, the laws preceded the thing, okay, who put the laws if that's going to create the P? They said, says Turok, we don't know how to create physics from nothing. 20 years later, you get the same answer. We don't know how to create something from nothing. And you're going to see that, you know, people like Larry, what's his name? Lawrence Krauss, Larry Krauss, he'll say the universe from nothing. And how can that possibly, how can you imagine a universe from nothing if you cannot justify or explain the mechanism? You know, please illustrate it. And of course they can't do that. It's just blah, 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 just a lot of wording. And they say, here's the equation. And that's it. That's all they have. And when you press them even further, they say, well, we don't know how to create something from nothing. You know, in the end, they all give you the same answer. So I don't know what all these people do for a living. All they do is just come up with nonsense. They make starting statements and people say, oh, the physicist, the scientist, he said this. And he's got to know because he knows all this math that nobody knows. So if he says that the universe came from nothing, it must be so. And obviously, you know, a lot of people like Christians, religious people, they like that to some degree. They just say, well, they just don't want to say that God did it. But we know that God was there and he created the first particle or whatever. Okay, so here we have the two areas, you know, so-called mathematical physics, supposedly science that stands against religion, and they have the same religion. They both believe that the universe came from nothing, that there was an origin to the universe. In one case you have God, in the other one you don't. You have this instanton, and when you ask them, what is the instant, how did that came into being? Well, they say it's an unreasonable question that you're asking. Love it. Just a question I needed answered, and they don't answer it. I thought that's what the dissertation was going to be about, right? Okay, where did all this nonsense come from? How did we end up with like this? Well, it all starts with Mr. Newton, okay? One way of looking at it, okay, here. We have Newton. He came up with his little equation, force equals mass times acceleration, his so-called second law, okay, of motion. Okay, you push the ball and it moves out, okay? So we have mass and we have acceleration. Straightforward, okay? What happened next, or I guess in the chronology, I'm missing a lot of intermediate steps, okay? I'm just going to go whiz through it real quick. We have Mr. Lagrange, okay, and he said, well, I can do Newton too, but I'm going to do it differently. I'm going to have this T minus V. And you say, what the hell is T minus V? Well, you have the potential energy minus the kinetic energy. And he was able to explain that to a great extent, in other words, not explain, but describe that, like in the case of a pendulum, if the pendulum goes up, at some point it stops. So you have no kinetic energy, and it's almost all potential energy, which, starts declining as you go in the opposite direction. Okay? But he was able to explain a lot of things using this vis viva, which was really the kinetic energy. So instead of talking in terms of mass and acceleration, they started talking in terms of energy and time. So that kind of changed, and new mathematics was developed. Okay? And they could explain the same things, or describe the same things in terms of energy and time. Okay? So that's 18th century, this is when this started moving along. Okay, what happened next? Well, here we have something was happening really in parallel to all this, and it's important to understand this to see how we got to the instanton. First, we have Huron of Alexandria, and I put Alexandria, okay, and he came up with the shortest distance for example, light, or the separation between 2 points. What unites them is a straight line, and that's the shortest distance. Fermat comes a few centuries later, and he says, oh, how about the shortest time? And again, he applied that to light. He says light travels in the shortest time possible. In other words, it travels straight, okay? Euler, Swiss guy, mathematician, he took some of these ideas, and he figured out that if you take the derivatives at maximum and minimum points along a curve, they are zero. And why? Again, because a derivative is a change in the rate of it's the rate of change of motion. Okay, and there is no rate of change of motion when you reach a zenith. Like when you throw a ball up, at some point it's got to come down. Okay, and when it goes up and it stops, well, at that point the rate of change is zero. Okay, so Euler came up with that. And then we have this fellow, William Hamilton. You probably heard of the Hamiltonian, just like you heard of the Lagrangian. And this is what these guys refer to. And what Hamilton came up with, which really is breathtaking, is stationary action. Stationary action. What does that mean? It means that you move while standing still. There is motion, but there's only location or position. It's static and dynamic and condensed into one. And so you say, how did he come up with that? Well, you see the red path there? What they do is they say this path has stationary action because mathematically you take its derivative and it's zero. Okay? That's essentially what these people are saying. And what, you wonder about people like Heisenberg, Werner Heisenberg. He came up with the uncertainty principle. It says that the more you know about more you know about position, the less you know about momentum, or vice versa. The more you know about momentum, the less you know about position. Again, that's along the same line of reasoning. What they're saying is that they don't understand the difference between standing still and moving. because, you know, when the ball stands still, it doesn't move. And yeah, the more you know about standing still, the less you know about moving. And the more you know about moving, the less you know about standing still. And Heisenberg got a Nobel for proving that mathematically. And it comes from these notions that these mathematicians invented, and they have little to do with physics. They have all to do with mathematics. So what happens next? Well, a lot of the mathematical physicists with quotations, that came after, started playing around with these notions. One of them was Paul Dirac. In the 1930s, he toyed around with this, but I'm going to skip over him a little bit and go to a person who really developed some of this to a greater extent, which was Richard Feynman. And it turns out that Feynman, you know, he was kind of like a young guy, but he was working at Alamos with a bomb. And in 1948, they had a little powwow at Pocono, Pennsylvania, a conference, all these people who worked on the bomb came over. A lot of them that worked on the bomb came over, and they talked about so-called physics, mathematical physics, okay? Especially about QED, quantum electrodynamics. And among the people who came, not someone who worked on the bomb, but Niels Bohr came, Paul Dirac came. The guy who organized it was Robert Oppenheimer, who was the guy who was in charge, the manager, the director of the bomb project. Okay, so all these people got together in Pennsylvania there, and they had a little powwow. And among the people who gave a dissertation was Feynman. And in the audience, again, we had Niels Bohr and Oppenheimer and Dirac and Wigner, Eugene Wigner, for those of you who know him. You know, they had all these old timers, and they were listening to this new generation of quantum mechanics. They didn't like it one bit. In fact, we have, what's his name, Jim Al-Khalili, and this comes from his mouth, okay? He's got, I'm just going to repeat what he said, okay? And he says the following, where is he? I can get it up here. Here it is. This is what Jim Al-Khalili says. He says, because he dared to visualize what was going on instead of using arcane, complicated mathematics, Feynman was describing what all his virtual particles were up to using his simple pictures, the so-called, Feynman diagrams, okay? There was an uproar. Niels Bohr, the father of quantum mechanics, leapt from his chair in disgust. He hated Feynman's diagrams because they were completely against everything he devoted his whole life to. You see, he believed that atomic particles could not be visualized under any circumstances. Feynman defended his new theory, tried to explain that the diagrams were simply a tool to help visualize his new equations, but the rest of the scientists, including Paul Dirac, wouldn't hear of it. They called him an idiot who understood nothing about quantum mechanics. Okay? And it's important to know that, good old Bohr and Dirac and Oppenheimer and all the rest, they didn't realize, but there was a revolution underway. And one of those people was Feynman, it was Schwinger and Tonomaga. Some of these people later on were going to win Nobel Prizes after the old guard was gone. Because what happened in the 50s and 60s, and really it starts taking off in the 70s, is that quantum changed altogether, completely. And nobody noticed. People like Niels Bohr and Werner Heisenberg, these people were particle people. They believed in discrete particles. They explained everything or described everything with discrete particles. Mathematically, it was pinpoint particle. That's what they were thinking of. The electron was a little particle. The photon was a little particle. And it was people like Einstein and Schrodinger and de Broglie. These were the people who were thinking in terms of waves and elongated things. Well, now you got the new generation of mechanics, people like Feynman. They come in and they said, look, they're bringing back the notion of continuity. Here you have constant interactions, and interaction leads to more interaction, and to more interaction and more interactions. So a photon breaks up according to Paul Dirac, into an electron and a positron. Then they blend together and they form a photon again, or release a photon. So they have this continuity. And what they did, since they couldn't explain action at a distance, what they started doing more and more were waves and fields. What you have is the the birth of quantum field theory. So no longer were they talking about little discrete particles, pinpoint particles that you could say, okay, this one's over here, that one's over there, and they didn't even know where they were. They just had this probability volume, a volume of probability, and that's where you could find the particle, somewhere in there. And there was a greater probability of finding it here than it was over there, that sort of thing. But these guys come up and they said, no, you're talking about a field. And the particle is really vibration of a field, localized vibration of a field, but the field extends all the way to the edge of space-time. So they were introducing a new concept here. They were introducing an elongated entity from a mathematical point of view. They were going to talk about fields, and of course, every now and then they put in the wave. Okay, so this was a revolution in the making. And of course, Bohr died in 1962, 65. They give a Nobel Prize to people like Schwinger and Feynman. Okay, because the new generation had now taken over. There was a revolution. Okay, so we have this little revolution. What was this revolution about? Well, Feynman is going to invent something called the path integral. Okay, and again, he's going to borrow these ideas from his predecessors, the mathematicians of the 16th, 17th, 18th century, and 19th century. These people came up with these notions of what? Of stationary action. And he kind of liked that. He says stationary action. It sounds like you can explain a lot with that because you don't have to include motion in there, and you treat 2 points, the beginning and the end point, as simultaneous. That's more or less what these people are going to do from a conceptual point of view. Okay, so it invents this path integral. You say, what's all that about? Well, you have this particle and moves from A to B. Very simple, straightforward, right? He's got his space-time diagram, okay? And particle moves from A to B. But according to quantum mechanics, the particle can go through any path. And it's even worse. It does go through all possible, imaginable paths. It does, in fact, go through all these paths. According to quantum mechanics, it takes all these routes to get from A to B, a quantum particle. Okay, so it's not only that it can, it does. And so you say, well, hold it, something seems to be wrong with that. I mean, you're saying, well, look, you have all these curves. Obviously, the one that goes in a straight line gets there faster than the guy going around. For example, take the photon. Travels at 300,000 kilometers per second. So if what was it? Heron says straight line. The other guy said Fermat says least time. Great, we've got it. And so you say, well, that's the least time. That's how the photon would go. So what is this nonsense about the photon going all around the universe just to get to B? Obviously, it would take more time. And then there was the issue of, what is all this for? What do we need this for? And so you need this, let me tell you why. Because quantum, you can talk magic. You can say anything you want. But then when you come to the real world, what is known as the classical world, the macro world, or our macro world, the world of anything above atom, now you have to interface your quantum world with this world, because there is an interaction. Light does interact with atoms. And so you can say anything you want about light in the quantum world. Just invent anything that comes out of your mind, that's fine, no problem. But now you have to relate it to the real world, because we do receive light, and we have to explain the interaction between light from the quantum world with atoms, many, of the real world. So there is an interface. So you have to kind of explain that and justify that from the quantum point of view. Okay, how did this particle from here go from A to B, B being, the atom where it hit or struck or whatever, or was absorbed? You got to explain that. You got to justify that in some kind of way. And these people don't do it physically, they do it mathematically. Okay, so this is what they had to explain, or these were some of the characteristics that they were addressing. Okay, some particularities of this path integral, why it was necessary, and other little quirks that we need to iron out. And so here's the problem. We had to approximate quantum to classical mechanics to explain actual, visible, measurable interactions. Okay? So this was a little bit of a problem for the people who were doing quantum. They had to relate it somehow to the real world in which we live, the macro world. You got to keep in mind, quantum mechanics is primarily a probabilistic theory. Okay? It's a probability thing. Okay, they work primarily out of probabilities because, again, it's a mathematical theory, which is not a theory. It's really a description. The theory is what's irrational. All wide-ranging, ridiculous itineraries happen, but have little probability of influencing the outcome. Only the sensible, with quotations, sensible paths are included. Okay, so what they do, all these other ones that go throughout the universe, they're not sensible. Even though they happen, they're not sensible, and the probability, the likelihood of them influencing the outcome is minimal or negligible or inexistent, you could say. So what they do is they get rid of these. They say, well, we don't care about that one. It's not that they're saying it doesn't happen. They say it does happen, but we don't pay attention to it because it doesn't really affect the outcome. That's their argument for that. Most itineraries cancel out anyways. For example, you can have destructive interference. One itinerary goes one way, the other one goes the other way, or they're in parallel, but they're offset. So they have what they call destructive interference, and so they don't affect the outcome either. And then to be consistent with special relativity, every photon carries its own clock and measures its own proper time. So you say, hold it. One of those curlicues went through the entire universe. Yeah, don't worry about it because, see, that's according to your eyes. According to the photon, it's carrying its own clock and it measures its own proper time. So this is another answer they give you. Then the other thing you got to keep in mind is that time under this mathematical scheme is imaginary. Okay? I call it irrational, they call it imaginary. Why imaginary? Because it's got square root of -1. There's no such monster. So anytime you see the square root of -1, that's replaced by the tiny letter I, and it means imaginary. And what they do a little mathematical footwork there called a transformation, and they morph this 3D plus 1 time, imaginary time world into a 4D scenario platform. Okay, so there's a lot of fudging around from a mathematical point of view to get this done, but they love it primarily because of that stationary action thing that Hamilton came out with, and that's why they always talk about the Hamiltonian. And you say, what the hell was that? Oh man, that's over my head. No, it just means that stationary motion. That's what it means. Okay, it means that when the ball moves, it doesn't stand still. When it stands still, it doesn't move. They don't know the difference between motion and location, in other words. That's the problem. And again, it's because they never defined any of these terms. All they do is mathematics, equations, and then they invent all these concepts to try to get their equation through. And this is what they work on. This is what you're paying your tax dollars for, to all these institutions that work on these things. Okay, let's find out how this works. Here's a visual representation I try to do for those so that you can visualize what they're trying to do. Let's assume you have a ball, a bunch of balls, okay? And you're throwing them against the wall. Think of them as photons, okay? In discrete particles. Okay, so here you have a whole bunch of particles and they're hitting some kind of barrier. Okay, you say, I understand that. They hit a barrier, fine, no problem. What should you expect from a photon? Well, you should expect a reflection. You know, the photons hit the barrier and they reflect. It turns out that when they do this with some quantum particles, it could be an electron, it could be photons, whatever, they realize that some of the particles go past the barrier. Okay? And you say, hold it, how did it go through the barrier? It's a particle, how did it pass the barrier? It's a physical barrier. And the particle goes right through. And so they had to explain this phenomena, or what they think is happening there. And for this, they needed this stationary action notion, because they have to explain how this particle ends up on the other side. And for this, it's very handy to have all these derivatives first, and also to have elongated entities such as waves and fields, because a field is not a localized entity, it's an extended entity. So that's when quantum field theory kind of takes off, because they say, hey, we like this, because now if we're going to explain something like tunneling, which is what this is called, we can use some of these notions. We can use this notion where a particle appears on the other side instantaneously first, and second, we can explain with a field why it's an extended entity rather than a localized particle. Okay, so this is what they're going to do. They're going to replace this notion of quantum with the field notion, or the wave, you could even say the wave notion, okay? Okay, so now what they can do with this is say, well, you know, what we do is we're just going to replace all this with waves. Okay, and so we have the wave coming in, and some wave goes through the barrier. Okay, so now that we're talking about waves, well, yeah, now you're talking about spirits. Okay, you can do anything with spirits. And so you can claim that, yeah, well, first of all, here you have that the only condition here is that they realize that the wave loses its amplitude. Okay, so when it goes to the other side, the wave loses its amplitude. But what they can claim now is that, yeah, you have particles coming in, and what you have on the other side is waves. And when you measure the wave, it collapses to a particle. Okay, so that's quantum in a nutshell. You know, as soon as you take a measurement, the field, the wave, whatever, condenses and collapses into a particle, and now you can take a measurement. Or it's simultaneous. When you take the measurement, it suddenly, you know, from every part of the universe, it condenses into this little tiny speck, and that's what you measure. And when you take it's like, you know, Mother Nature, Father Universe, God, the devil, whoever is watching you and saying, oh, he's going to take a measurement. Yeah, I'm going to take a measurement. As soon as you touch the thing, they go hocus pocus, and the whole thing, you know, draws together and condenses into a point. You say, hey, it's a point. Every time I measure, it's a point. As soon as you take the measurement away, whatever you're measuring, it goes back to being a wave, a field, an extended entity. And yeah, with this, obviously, you can get around a lot of questions, because anyone who asks you, you just give them that answer, and the person says, well, I still don't understand. Well, you got to take math. You got to go through all the pain I went through in order to understand all this nonsense, okay? That's the way it works. Okay, so let's continue here. When all is said and done, what is all this instanton about? Well, it's what is the definition? What is an instanton? How does it fall in with all this? Well, an instanton is a classical solution to an equation of motion with finite non-zero action. A solution to the imaginary time. The first one was, I think, from the Wikipedia. The second one is from a Cambridge site, physics site. A solution to the imaginary time nonlinear field equation of Yang-Mills field theory carries information about quantum tunneling. So what is it? It's a solution to an equation. That's what an instanton is. So what was this nonsense that Turek was saying that it looks like a P? We got a little problem here, because here these people are saying it's a solution, which is a concept. They're saying it's a solution to an equation, to a problem or whatever, okay? And this guy says, yeah, it looks like a P with little dimples, and it's got a big nose, and it looks like Santa Claus, I guess. I don't know. why did they draw it? If they're talking about a solution to an equation, to a problem, what does that have to do with physics, with an object that we're staring at over there? Well, they had to do this because they have to explain why time and space did not have an origin from a pictorial point of view. And they say, well, imagine it as a circle. And so it's got no beginning and end. And so that's how we do it mathematically. And when we extrapolate our mathematics to the visual world, this is what we come up with. Some kind of P that has space and time wound around it, with no beginning or end to space or time. And so this is how they end up saying to you that space and time came out of nowhere, because they didn't need a nowhere, because it's like they were there all the time. The circle was always out there, and you can't imagine where time and space start on a circle. That's their reasoning. That's how these people look at this. Okay. Okay, here's the Cambridge. These are the followers of Stephen Hawking. This is what they put in their site, okay? And this is essentially their summary of this cosmological instanton. This is what is today, okay? So this is actual, okay? This is what they're working on. This is what they spend their time on, calculating and doing equations on this nonsense, okay? During inflation, quantum mechanical vacuum fluctuations are amplified. Okay, and due to the accelerating expansion of the universe, they are stretched to macroscopic length scales. In other words, they have to explain how the instanton has something to do with the beginning of the universe. Okay, so that's where they're putting it in there. And again, you got to keep this notion of static motion, static dynamics, I guess you could call it, stationary action. Whatever that means to you. Uncertainty principle, when it moves, it doesn't stand still. Or maybe it does both. Who knows? Okay, and it says, later on, when the universe has cooled, they seed the growth. So you have these vacuum fluctuations. They're going to seed the growth. They're going to pump the energy of the universe so it starts getting bigger, of large-scale structures. Example, galaxies, like those we see today. And here's the proof, the evidence. One sees the imprint of these primordial fluctuations as small temperature perturbations in the cosmic small microwave background radiation, the CMB. So that's the proof. They say, look, when you see these vibrations, that's the vacuum fluctuations from the instanton that started our universe. Okay? That's the origin of space and time. From where matter eventually arose, right? We saw that the other day. Since different types of instantons predict slightly different fluctuation spectra, the temperature perturbations in the cosmic microwave background radiation will depend on the instanton from which the universe was created. How do you like that as a bedtime story for babies, okay? Yeah. Some of these people really have some fancy notions. Well, all I can do is give you my summary. Okay, so here's Bill Gates' summary on the so-called instanton that gave the God particle that gave origin to the universe. Okay, this is what I think of it. Okay, pseudo particle called instanton because it's a pseudo quasi particle because they're all quasi. The quasis, the quasis and the pseudos, okay, called instanton from instant. That's where it comes from, okay, because it happens in an instant. There's essentially, what is it? Stationary action, okay, is a solution to an equation. That's what it is. That's what they all do. That's what they're all trying to figure out. They're trying to look for an equation that will give them essentially the unification of all forces, all four forces. So far they have supposedly the electroweak. Now they're trying to incorporate, first the gluon, the strong force, and then the graviton, the gravitational force. It was invented to account for action at a distance phenomena that quantum mechanics will never be able to explain with discrete particles. The instanton solution, okay, that's a solution only, is a stand-in for what? Stationary action. That's what it is. That's why it's instant. They're saying there's motion, there's action, there's whatever, but it's instant. It's in a single frame of the universal movie. The instanton, in effect, treats start and endpoints as simultaneous. That's essentially what they do. But they do it through a mathematical trick where they say, well, we're going to take the derivative of this length. We're going to treat it as almost a straight line, or the average of that straight line. We're going to take the derivative, and the derivative is 0, so we have no motion. We have no change in the rate. Okay? So that's the notion in general terms. The instanton comes in handy to explain action at a distance, phenomena such as tunneling and what? How the universe came into being instantaneously without a cause. And what's my corollary? The instanton gives job security to a generation of mathematicians that have nothing else to work on. That's what you're paying for. That's what your tax dollars are going into. Okay? So that's the end of the instanton for today. Okay, folks, let's look at some of the questions and comments people made. Let's go with the first one here. Okay, a fellow says, related to, I guess, last week, beyond human visualization or imagination, there is no reality. This is conclusion of what you talk, or I guess he's affirming that. And no, you got it wrong, okay? And this is, again, people have it all wrong. Why? Because they introduced an observer. So he's saying, what you're saying is what you visualize, what you imagine. No, that's not reality. Okay, so let's clarify that very clearly, okay? Let's make it obvious. So here it is. Here's my answer to that. Okay? Oh, come on. Reality has nothing to do with what? Human, observers, visualization, imagination, observation, tangibility, perception, feeling, consciousness, verification, experimentation, proving sensations, etc. What we do in science, we define the word reality to begin with so we know what we're talking about. What is reality? It's a synonym of exist, actual, real, etc. What is it? An object plus location. What is it? What I synthesize as, what is it? I forgot the term now. Essentially, you need an object and it has to have location. Physical presence, that's what I was thinking of. Okay, physical presence. So, no, reality is not what you perceive or imagine. In reality, you have to define the term. And I define it. You need an object, and that object has to have location. Then you have reality. Okay, that you can say that object is real or that object exists. So it's not what you visualize. I can visualize God. That doesn't make him exist. I can visualize or imagine a chair. That chair doesn't exist. A square doesn't exist. Okay, and I can imagine a square also. But that square doesn't exist. Neither the one that I wrote on paper. What exists is the ink and the paper, but not the square. The square is an object because it has shape. That's the only condition for the word object. It has to have shape. That's it. Does that square exist? No, squares don't exist. They have no location, so you won't find one out there in space. Okay, so don't look for it. Okay. Square is that which has shape, and therefore it's an object. Period. That's the definition of object. It applies to any object. It's the only property, attribute that all objects in the universe. It's the universal property of all objects. Shape. Not all objects can be touched. Not all objects can be seen. Not all objects exist. And the only property, again, is shape. Okay, so that's it. Anyone who doesn't like that, you don't have to agree with me. The only way you can overcome that is come into the ring with your own definition. You have to have a definition for object, otherwise you can't talk about object, and we shouldn't even listen to you, right? Because if you don't have a definition for the word object, which is absolutely necessary in physics, because physics cannot be done without objects. Physics is the science that deals with objects. Okay, you wouldn't have anything to study or analyze or whatever. There were no objects, so you need to define the word object for the purposes of physics. So before you can attack my definition, you have to put your definition. It's just that simple. If you don't have a definition, you can't even talk. You got to shut your mouth and listen. Only when you have a definition that applies to all objects that you can use consistently, scientifically in physics, then can you bring it in here. Okay, so that's where it starts. Okay, another issue, again, more or less related to what I talked about the other day. Okay, and the fellow says, God as master, designer, and creator is not a belief, faith, or religion. Oh, it's a logical conclusion. Everything beyond that is a theory, opinion. Oh man. So many errors in just a couple sentences. Okay, let's find out if we can find out all the errors in here. Okay, yeah, obviously a person has serious problems, right? Okay, so let's find out. Here it is. If God is designer and or creator, then God is an object by definition. What is an object? That which has shape. God is not a concept under that if he's master, designer, creator. Why? Because a concept is a word that embodies two objects. That's the short version. Okay. So God is an object. And there you see God creating the universe. He's the designer. He's the creator. You can see something there for God, right? There is a shape. So if God has shape, God is an object. You're treating God as an object no matter what. And again, if you don't like the definition of object, you have only one recourse, and that is to define the word object. Come into the ring, defend your definition with sword and shield. Okay? And God is not a logical conclusion. It's known as an assumption. You make an assumption, say, let us assume God is that fellow that's down there with a magic wand. Okay, so you're saying that, you're imagining that God is an object, okay, a thing. And in this case, because he's got shape, okay, so that's the first condition. And then if you want to say that God exists, all you have to say is he has location. We will assume that God has location. What do we mean by that? It means that you can establish a distance between your chest and God's chest, or between your eye and God's eye. There's distance between the two of you, and God has location with respect to the other matter in the universe. That's what we mean by God exists. God has to have location if he wants to exist. Okay, so it's not enough for God to be an object. God must, in addition, okay, have location. And then a theory is not an opinion like this fellow says. That is a theory, opinion. No, opinion is religion. Theory is an explanation. Okay, so no, theory is not an opinion. Religion is opinion. Okay, so let's make sure we separate those. Okay, let me get back in here. And next issue, next question, next comment. Fellow says, survey says, you can simply Google physics definitions. Because I asked them to go and look for definition, a scientific definition of the word object. I think concept exists. Okay? So he had to go out there and look for a definition, a scientific one, from a scientific dictionary. Because he says there's scientific dictionaries out there, and he says they don't agree with me. Yeah, I don't care if they agree with me or not, that's irrelevant. We want to make sure that they make sense and that they can defend their definitions. And if someone vouches for those definitions, it's he who has to go into the ring and defend those definitions for the dictionary. Okay, and if he doesn't know enough, he's got to do his research and find out how he's going to defend that definition. He can't just transcribe a definition from the dictionary and says, oh, this is the one I'm going to use. No, if it's an irrational definition, you don't want to use it, for sure. Not in science, at least. And he says an object has to be three-dimensional. You know, there are objects that, again, we don't know until he's going to define the word object. We don't know what he means by that. You know, why he comes up with this criterion that an object has to be three-dimensional. This is arbitrary, and it's got to be founded on a definition of the word object. And again, since he didn't put a definition, a scientific definition, we don't know what he means by the word object. Therefore, it's very arbitrary and opinionated to just say it's got to be three-dimensional. And again, three-dimensional is the notion of ordinary speech, not a scientific definition. Okay, so keep those in mind. A rock is an object that doesn't experience existing, hopefully. You didn't need to say that. I'm sure a lot of people, I mean, I don't know your asylum if the rocks have experienced anything, okay? A circle, square, triangle are not objects or concept. We call them geometry, okay? Whatever objects, whatever you mean by object. You have to tell us what an object is before you make that statement, okay? Until you can tell us what an object is scientifically and defend that definition, you got nothing. Shadow is a two-dimensional geometry casted from an interference of light by an object. Yeah, what I said is shadow means blocked light. And there is no physical standalone object called blocked light, aside from the fact that a shadow has no starting point. I mean, if you're going to talk about shape, shape is all around. Okay, that's shape. And no shadow has shape all around. Okay, what shadows have, they start at the feet of whoever's getting the shadow. And even if you take like I showed the other day, even if you take a light and point it in the middle of a space at I don't know, a planet, and somehow you project that onto a screen, okay, that shadow comes all the way to the planet. So it starts at the planet. It's not that it's just standalone out there. That shadow is blocked light, and blocked light goes all the way from the object that's blocking light all the way to the shadow. So again, it's not an independent thing, and second, it doesn't have shape, because shape extends all the way to the object. Okay, so it's a three-dimensional shape, you could say, but even that is not a shape because it's not standalone. Okay, shape means you got something there, and you can see it, independently. And you can't do that with a shadow. Shadow goes all the way to your feet. Prove that to yourself. Go out into the sun one day, and you'll find out that the shadow, the feet of your shadow go all the way to your feet and extends all the way to your body. There is no such thing. And in that case, the light that's being blocked is, slanted in some degrees, because it goes from your head downwards. So all that space between you and your shadow, your two-dimensional shadow there, all that three-dimensional volume, that whole thing is the shadow. It's called the penumbra or the umbra, depending on which portion you're talking about. Okay, so here's the answer, formal answer to this gentleman. And here it is, okay, all the things. None of these are definitions. These are examples without any foundation or unscientific opinions. That's all he's got there. When Googling definition of object for physics, we find the following. We find a Wikipedia. You can do this on your own. You don't have to take my word for it. Just Google definition of object, or definition of object for science or for physics or for whatever, and you'll find this same thing I found. And find Wikipedia, an object is an identifiable collection of matter, which is the definition this fellow used the other day. Again, he took it from the Wikipedia because there is no scientific definition of the word object. Then another one you'll find is one in Hub Pages. A guy says, what is an object for physics? And he's got the same definition that I have. And there you find the link so you can look it up. And that'd be nice if this fellow would put links instead of just giving examples and just giving his opinion. I mean, if he's got a scientific definition from a scientific dictionary, all he's got to do is put the link and we'll check it out. Okay, so if he can't put a link, he doesn't have a scientific definition from a scientific dictionary. Okay? And then the last one there, object, anything that has no internal structure. That's what Bozeman's science came up with on YouTube, and there's the link. You can look it up. So again, he says the only object that exists essentially, or that is an object, is an electron. Again, no internal structure. What is structure? Is a synonym of object. And what is anything, which is the word he used, also synonym of object. In other words, this fellow who runs his Bozeman site, he has no clue whatsoever. Okay? He doesn't know what an object is for the purposes of physics, because he would not be able to defend that definition. He just said it. Okay? And so, yeah, there is no scientific definition of the word object. And the only way you're going to show it, one of two ways. Either put a link so that we can check it out objectively and see what that definition says, and see if that definition can be defended, because you got to defend the definition. It's not just saying, well, this is what I found in a dictionary. What's that? That's nothing. You got to defend it. Otherwise, it's worthless, endeavor. And then the other one is, write your definition, whatever definition you think it is, and again, be able to defend it. And so far, this fellow has not come through. He has not been able to do that. Okay, here's another common question issue. Fellow says, rational science is also, I think it's the same guy, rational science is also based from belief. Believing science doesn't include observation, experimentation, geometry, mathematics. Well, for this, again, you have to define what we mean by science. Okay, that's all you got to do. Once you define the word science, we know what we're talking about. Okay, here it is. We have a definition, and you don't have to agree with it. Again, all you have to do is challenge it, and the way you challenge it is producing a better mousetrap. And the way you do that is saying, look, I've got a better definition than you do. Okay, defend it. Okay, here it is. Okay, here's our definition of science. Okay, rational explanations. That's it. That's the definition of science. Okay, and it's divided in two branches, philosophy and physics. One deals with objects, causes and mechanisms. The other one primarily with reasons and purpose. Okay, behavior. We're trying to explain behavior. Okay, and here's a final point on that one. Just a kind of like a summary. Okay. And so you have science, rational explanations divided into those two regions. Okay. Now religion is just opinions and beliefs. That's what it is. Okay. If you have just an opinion, a belief, you have a religion. And we all have a religion, by the way. We all have beliefs. We all have opinions. We just have to distinguish religion from science. Okay. And now in science, we do not use the senses because the senses makes it subjective. So we do not do experiments. Why? Because science is rational explanations. We don't care how many experiments you did, and it doesn't matter if you did because it doesn't mean you understood what you did. So who cares if you did 100 times, an experiment 100 times, if you cannot explain what you did? What are you going to do? Just describe the experiment and say, well, I dropped the pen 100 times and it always fell to the floor. Oh, great. I mean, so is the experiment part of science? No, the part of science, the juice, is the explanation. If you can explain why, the cause, the mechanism of why the pen fell to the floor, then you have science. Otherwise, all you have is an experiment with ignorance. Okay? We don't have truth, fact, or knowledge, proof. We don't present evidence because we're not trying to convince anyone. I mean, you can introduce evidence, but that's part of religion. Okay, that attacks belief, opinion. We have no use for consciousness, sensations, perception. Again, we don't use the senses because the only sense we use is common sense, the least common of all senses. Okay, and then you have irrational explanations. Are those all on the right? You have specifically the ones that I want to mention is theism, atheism, and agnosticism. All those three are irrational theories, because they rely on belief, on religion, on what's in the center there. And same for mathematical physics. Whether you do general relativity, quantum mechanics, or string theory, all you have is an irrational explanation for how this universe works. Okay? And irrational is distinguished from supernatural. In that supernatural, you can imagine the objects. You can imagine God. You can imagine an angel. You can imagine the devil. Okay? What you cannot imagine is the mechanism. In the case of mathematical physics and atheism, all these, we have something different. We cannot imagine the objects. Okay, that's the problem. They don't have objects. What they have is concepts. They're moving concepts around. They move energy, and they move fields, and they move waves and vortices and ether and all these other plasma, all these other concepts. And they say, I'm moving plasma. Now, you can't move plasma because plasma is already in motion. You can't move what's already in motion. Okay, so yeah, they're moving concepts, especially dynamic concepts around. They don't even realize that. So they talk about ether, plasma. They talk about energy and fields as if they were physical objects, and they don't realize that these are all mathematical concepts. With that, I'm going to see you on Sunday.